got through, what is this? Is this 33B? Is that what we got through? What's the title of this? 33A. Yeah, we did 33A, and so that was due today. And 33B wasn't due today, but actually we knocked it out too. So I'll show you what I mean. So this is 33A. Oh, go back. I wanted to go back because I want to underline degeneracy pressure, because I feel like, was this Monday? I feel like Friday we kind of got, oh, my thing's not working. Anyway, if my pen were working, I would underline degeneracy pressure. If I draw, so what do atoms look like? What's the center of an atom? Nucleus, very good. So here's the nucleus, and what two things do we have in there? Yep, protons and neutrons. And I'll go ahead and make a 0 for neutrons and a plus for protons. And then what do we have outside here? Electrons. And it is amazing, drawn to scale. If you read some things, I mean, atoms are very small, and nuclei are very small, and then actually the electrons relative to the size of the nucleus are really pretty spacious. Do you know what I'm saying? They buzz around. It is so cool. So most matter, so that if this is kind of the electron, the edge of the electrons, okay, I'm going to try to, and you guys are some really great artists, by the way, in here. I'm going to draw another electron, and this is my nucleus over here, okay? So these are two normal atoms that are bumping up against each other. And basically, this atom with its nucleus and electron, and this atom with its nucleus and electron, thou shalt not come into each other's space. And so kind of that's what's being shown down here. So it's called degeneracy pressure. So just normal degeneracy pressure. And I should say, I'll go ahead and call it, I think this would be called electron. I'll just put, electron degeneracy pressure. Thank goodness for the electrons, because that is actually why, how do I say? Okay, so we have a plastic marker here, a little outside marker, and we have a stylus here. It's kind of metal. Now each of these are made up of atoms, and there's a lot of empty space between the nuclei of the atoms. Okay, and I cannot pass one through the other. And the thing,
magnetism, and so
it
is.
is.
You have a negative and a positive del.
There is, and I think I've heard it put that way. This electron associated with this atom and this electron associated with this atom are the fact that they're both the same charge, they repel each other. So right. Yeah, they will not. They will not. Okay, yeah. And so what that has to do with stars is that when our sun was getting ready to, when our sun was kind of doing its thing, before it was the sun, it was a proto-sun, okay? It gathered most of the material that made up the solar nebula, right? And before it had solar wind, before it turned on, it basically, most of the matter kind of kept coming together. Most of the matter was hydrogen and helium, okay, the solar nebula. And so my point is that as it came together, it could only squish together as much as electron degeneracy will allow it. It stopped. It couldn't squish anymore. But good for us that it squished enough that it created the pressure and the temperature that was required for nuclear fusion in the core of the sun. Okay, so that's it. That it stopped. So the thing with failed stars or brown dwarfs are they start out in a nebula, okay, and they have a certain amount of mass that's going to be theirs, and it's going to come together, but it stops. It doesn't have enough. It has to stop electron degeneracy too, but its pressure and temperature aren't sufficient to begin nuclear fusion. It's a failed star. It's a brown dwarf. Okay. And the limit for that is what we say 8% or 0.08 times the mass of our sun. 0.08 times the mass of our sun, it can begin nuclear fusion at its core. Less than that, it doesn't. It gets nice and toasty, but then it just kind of dies away. So then actually, this is in, these are brown dwarfs, and I don't know where they are. To me, these aren't brown dwarfs because these are the trapezium. These are nice bright stars, but there are brown dwarfs. This actually, finally, I can see, well, because they circled them, the brown dwarfs that were found by two different sources, kind of the red and the blue circles are dwarfs. So failed stars. So anyway, this actually was, and I'll prove it to you because I looked at it today. The parts, you know how it's divided out there up in canvas? This was my brown dwarf part. So actually I had something called 33B, and we just did, this is Orion, this is the circles, this is the one that we also did on Friday. Okay, so anyway, 33B is also due, or will be due on Wednesday. Okay? So we're going to stick in order, I think, and the next thing we're going to talk about are, and I couldn't think of the name, but they're called extrasolar planets. I think I totally butchered the name. So we could have covered this in various places, but I want to cover it under stars are being born, because as stars are being born, we can actually see that they have disk-like material around them. We can have, it's called accretion, where planets can form around other stars, and those are called extrasolar planets. So I have a little video, I have a few videos. Let's see what this one does. And my sound's working. Pretty exciting. Oops, okay. Come back. So I have a few slides to show you, just kind of pictures of looking at protostars. So what's a protostar? Star in the making, exactly. So these are stars in the making. You can kind of see a little bit of disk material around them where planets can form. So again, the way we understand kind of the way stars are born and planets are made is to look at kind of stars and planets in various stages of being born. Again, protoplanetary disk. What is a protoplanetary disk? That's that kind of disk of material that planets can be formed in around a baby star, a protostar. Pretty cool. Again, now you never know when you're looking if it's a figure or if it's a photograph, but here's another photograph, and we're looking at it. This would be what's called face-on versus edge-on. So face-on, you can see these little lanes that are developing where the material can be squished together via accretion and make into a new planet. Is that not awesome, or what? This is kind of showing you what we saw in that video just a minute ago, the idea of we really don't see many planets orbiting stars directly. We see them indirectly by the two methods that they described. And one of them is, I liked where it had kind of had the star and then it had kind of being tugged by two planets like little kids. Okay, so the star gets kind of tugged. Basically, a lot of times the star is orbiting the same common center of mass that the planets are. So the star is going to do kind of like a little loop-de-loop, depending upon the planets it's got affecting it. So here we see, you can't really see, okay, here it is, the unseen planet that's affecting the fact that this star actually orbits this center of mass. So this is the star at two different locations. And you guys told me as it's moving away, we have a red shift, and as it's moving towards, we have a blue shift. And that's exactly. But is this right? The thing about this is a similar problem with the eclipsing method is that it has to be kind of, we have to see it edge on, because if you see it face on, okay, you're not going to get that Doppler shift. So we still have, it's not easy. This is the eclipsing method that the video talked about. Under here, this yellow here, or orange here, we have the light curve. So when the planet and the star are both being seen, we're at maximum light, okay? And then when the planet goes in front of the star, we see the light dim down a little bit. So. Now I have a video to show you here just because, I don't know, I thought I was interested. We've talked about the Hubble Space Telescope, and this kind of reminds me of the Hubble Space Telescope, but it's so not the Hubble Space Telescope. The thing that's similar is you can kind of see the solar panels. This is the Spitzer Space Telescope, and it is no longer collecting active data, but from what I can tell, they are still sifting through all of the data that Kepler sent back. So let's check out this video right quick. You don't have to watch science fiction movies to know space can be brutal. But like the missions to Mars, it's interesting to hear all the plan Bs, plan Cs, plans Ds that they come up with. I don't know. It's pretty cool. So Kepler is no longer, as far as I know, it's sending new data, but there's a delay in when we get the data versus when it's processed and we know. These dots each represent extrasolar planets. The yellow dots, let's see, wait, first off, along the x-axis we have how long it takes for the planet to complete one orbit about its star. Okay, these are kind of interesting, how many days it takes to complete the orbit around its star. Along the y-axis, we have how big is the planet relative to the Earth. So right here, let's see, where is it? Yeah. It looks like these both look like ones. Oh, there's a 4. Goodness, it looks like a 1. This is 1. So this would be the same size as the Earth. This would be 4 times the size of the Earth. Okay, 10, 20, 40. So over here we have 4 times the size of the Earth would be, we'll end up with a Neptune. A little above 10 would be Jupiter. So you can kind of see we have definitely a cluster of stars around here, the size of the Earth. And orbiting its star, though, this kind of threw me off. That's a pretty fast orbital period. These are in days. I don't know. If we look at this slide together, we kind of see this is looking at the size of the planet, again, relative to the Earth. So if you find this 1 right here, this is 0.7 to 1. This is 1 to 1.4 times the size of the Earth. These would be like Earth-sized planets. And so clearly we have more, and then this is how many were that type. So, and then up here along on the bars are how many extrasolar planets are fall in that range that were found. And this is of the first 2,213 extrasolar planets that were found. So if I could have my stylus work, I could draw a line right here, and these would be smaller than Earth, and these would be larger. And up here, we kind of have the gap of, up here we have the planets in our solar system. Of course, they're not in order from the sun, but they're in the order of size. So it's interesting how these extrasolar planets are kind of, we don't have planets that size. This one is looking at extrasolar planets. Again, the planet size, and then here is the average number of planets per star. That one doesn't make sense to me because we have a fraction. I don't know. You've probably heard of the Goldilocks zone before, and this green zone is like the Goldilocks zone. This is the habitable zone. So, of course, one thing we're interested in is as we look at these extrasolar planets, are these planets that there could be life on? And the big thing we're looking at is with regard to water. Water needs to be able to hang out in its liquid state. So it can't be too close to the sun or too far from the sun in order to have water in its liquid state. So the habitable zone or these green zones or Goldilocks zones, they all mean the same thing. So this kind of wraps it up. It shows a kind of a really pretty picture of maybe what extrasolar planets, terrestrial planets, similar in size to the Earth, might look like. That's all I have for this part. So let's see. Yeah, we're going to go ahead and this is a nice video that I was talking about the lives of stars. We're going to watch the very first part of this, maybe 10 minutes of it or so. And then we'll watch the rest on Wednesday.